Reduction formulas. Okay, also known as recurrence formulas. So you might see them sometimes called that. Basically, it's when you've got the integrand, but it's raised to some power. And the idea is you try and reduce the power down to get a simpler integral to do. You'll find that a lot of the times integration by parts is used. That doesn't mean they always use it, but it's quite a common way of doing these ones. So let's do this for an example. It starts off, the power is given to us of 3, so we want to find the integral from 1 to e of this one. We got two functions multiplied together. One's not the derivative of the other, so yep, okay, we'll go with parts. But let's create a formula for it. Because the power is 3, we're probably going to have to do repeated integration by parts. So once that power starts getting big, now it's debatable whether 3 is big or not. But once it starts getting big, sometimes it's easier to come up with a formula, a general formula for the power of n, and then you can just apply the formula until you get it down to something simple. So let's try and create one for this. We'll make it log x to the power of n. But as I say, we're going to have to do it by parts. So u is going to be log x to the power of n. So we get n log x n minus 1 over x dx, which means the v is x dx. V becomes a half x squared. So we have uv, half x squared log x to the power of n going from 1 to e, minus, now the constant when we pull all that out, for the v du we've got n on 2, so that goes out the front. We're left with x log x to the power of n minus 1, which you'll see is the same integral as our starting point, but the power has been reduced. Now, I can work the first bit out. Let's sub in the e, we sub in the 1, we get e squared on 2. And so there's our formula. E squared on 2 minus n on 2, I n minus 1. So now I can use my formula, because what we've got is I3. So using the formula, I get e squared on 2 minus 3 on 2 lots of I2. But then I can use the formula to find I2. And I2 would be e squared on 2 minus I1, playing around with that one. I1, well, apply it again. We get e squared on 2 minus a half I0. Playing around with that, we got 3/4 I0. I0 now we can stop because that log function now is to the power of 0, and anything to the power of 0 is 1. So now all I've got to find is the integral of x dx. Add 1 to the power over the power, sub in the e, sub in the 1, and we have our answer. So whilst, alright, it might have been a little bit of time consuming coming up with the formula, but it did mean we didn't have to use integration by parts. How many times would we have had to do that? 3 times for this one? Now, I've done the answer by reducing down. Some people like to build up. So I have seen it done that way, where they start with I0. And so work out the I0, and then from there we know, well, I1 is e squared on 2 minus half I0. So we build it up, but that's I1. So then we build it up into I2. And we want to keep going because we want I3, so we build that up and come up with the same answer. I guess it's a preference. I like the first way myself, where we reduce it down, but some people like the building it up way. Integration by parts, yep, most common, I probably should have said, is the most common way. But this one here, I don't need parts. I can just play around with trig identities on this one. So in is going to be the integral of cot to the power of n. So essentially we've got to find the integral of cot to the power of 6, is what this question is saying. Now, remember when we looked at the trig integrals, it didn't matter what the power was, whether it was odd or even, we used the same technique. So I'll use that technique for power of n. And if you recall, that technique was pull out the cot squared, then that way the cot squared can become cosec squared minus 1. I can split that into 2 integrals. The first one now has function times derivative. The second one, you'll note, is the same as my first, but the power has been reduced. So let's do the first one. Oh, well, do it by substitution. U equals cot x, du is minus cosec squared. So I have minus integral of u to the power of n minus 2, add 1 to the power over the power, sub the u back in, and we've got a formula. I6 is what we now have to go and find using that formula. It works sometimes, but I'll show you it. When you got trig, because trig identities involve squares, And if they've given you the formula and said, I'll show it's this, and you notice that the power is reduced by 2, then sometimes if you play around with in plus or minus in plus 2, you can come up with it. So for this one, I could have gone, well, in plus 2 is cot to the n plus cot n plus 2. Join those together, factorise out the 1 plus cot squared, and I've now got cot to the power of n cosec squared, which is add 1 to the power over the power, and I've now got my formula. Because I can move the in over, well, that's a formula for in plus 2. If I want to turn it into a formula for in, everywhere I see an n, I replace it with n minus 2. So it becomes in cot to the power of n minus 1 and so on. So, yeah, look, it's a rare way of doing it, but occasionally it can be done that way. It's another way of approaching it. All right, so back to what we have to find. We have to find I6. So let's apply it. We get minus a fifth cot 5 minus I4. Now we can use our formula for I4. And we've now got I2. Use the formula for I2. We've now got I0. I0 will do us, because again, we're now going to have power of 0, which is 1. So our integral is just dx. And that is, of course, x. There's our answer. Here's an example where, yes, integration by parts, but algebraic manipulation, trig identities also can come in handy. So in is the integral of 1 plus x squared to the power of n. They're telling us our formula is going to connect in with in minus 1. Okay, so I've got 1 plus x squared to the power of n. I'm going to let u equal that. So du becomes 2nx 1 plus x squared n minus 1. V is dx, v is x. So uv minus 2n in this case, v du. Now have a look at the integral. This is where I'm going to use the algebraic manipulation. I've got x squared times 1 plus x squared to the power of n minus 1. So if I make that 1 plus x squared minus 1, split that into 2 integrals, the first one now becomes, when I recombine the 1 plus x squared with the 1 plus x squared to the n minus 1, 1 plus x squared to the power of n. The second one is 1 plus x squared to the n minus 1. So I actually have that in is x, 1 plus x squared to the n minus 2n in plus 2n in minus 1. Think of it like an equation. We want to make in the subject. So we move the 2n over. Now, some would say that's good enough for a formula, right? Because it's got it as in equals. Yes, there's 2n plus 1. Some people like to divide by the 2n plus 1 and come up with a formula like that, so it's simply in. But as I say, sometimes you might see the formulas written where it's not just in. There might be some multiple of in that you have to prove. HSC, let's have a look. 1987. Whoa. Given that in is the integral cos to the power of n this time, prove that in is, and they have our expressions, differs by 2. Maybe I could play around with that other idea that I had. Cosine, odd or even? Well, it depends on how I approach it. Whether odd or even. I don't know whether n's odd or even. In fact, sometimes it might be odd, sometimes it might be even. Now, they want us to find cos to the power of 5, which is odd. Maybe that's a hint, but I don't know if I want to gamble on that. So cos to the power of n, let's pull out the cos. Now I'm going to do it by parts, because as I say, I don't know whether n's odd or even, so I really don't know whether I'm going to use a double angle or whether I'm going to use the 1 minus sine squared. I don't know. So let's do it by parts. So u to u minus n minus 1, etc. So v becomes cos x, v is sine x. So uv, sine x cos n minus 1, minus v du. But in this case, du is negative, so we end up with plus. Now let's have a look at our integral. Cos n minus 2x sine squared. Well, the sine squared I can rewrite as 1 minus cos squared. And I can also evaluate the first brackets there. I'll do that. And that just turns out to be 0, the first brackets when you look at it, because of course the cos pi on 2 is 0, but in the next one, the sine of 0 is 0. So it's all 0. I'm splitting my integral up into 2, and they're both now cos to the power of something. So I can say, well, that's n minus 1 in minus 2 minus n minus 1 in. Think of it like an equation now. We'll move the INs to the other side, and I get NIN. Now, in this case, I can't leave it like that because they've told me to prove it's a certain thing. So divide by N, we've got our result. Differs by 2. Let's see how we go with that one. So I'll go IN minus 2 minus IN. Let's see what happens. So subbing into that, cos n to the power of n minus 2 minus cos n, I can factorise and get 1 minus cos squared, which is sine squared. U equals sine x to u is cos x. I'm still going to have to do it by parts. So I don't know that this time that technique really is that useful. It's still got a fair bit of work to do there. But we'll keep going with it. uv, it's another one where that's just going to be 0, isn't it? Because we've got the sine, cos and those limits. But the other integral is 1 on n minus 1 integral of cos n, which is 1 on n minus 1 in. Now think of it like an equation. Get rid of the denominator, multiply minus 1. Eventually, there you go. We get the same one. So, okay, let's go work out that I5 that they want. I5, 4/5 I3, which means then 2/3 I1. I1 is cos x. I can't go to I0 this time because we're reducing by 2. So I have to stop at I1. You can't go to I negative 1, by the way. So cos goes to sine, sub in. We've got our answer, 8/15 as our answer. All right, now for a beauty. Strap yourself in. Okay. In is going to be the integral of tan to the power of n, and jn is going to be minus 1 to the power of n times I2n. They're actually giving us the hint this time, use the idea. So they're telling us, show that in plus 2 is 1 on n plus 1. So okay, we get integral of tan to the power of n plus integral of tan n plus 2. Join those together, we've got 1 plus tan squared, which is of course sec squared. Derivative times function. But if you don't see it, u is tan x, du is sec squared. And but if I am going to do it by substitution, I've got to fix my limits up. So I get integral from 0 to 1 of u to the power of n, add 1 to the power over the power, sub in the 1, sub in the 0, and we get the required result. Deduce then that jn minus 1 must equal this expression. Well, jn, remember they gave us a definition for jn. There it is. It's minus 1 to the power of n I2n. So, jn minus 1 to the power of n I2n. Jn minus 1, well, wherever I see an n, replace it with n minus 1. So it becomes minus 1 to the power of n minus 1, I, 2n minus 2. So I've turned it into a plus. Okay? So now I've got minus 1 to the power of n. Because I see the answer's got it, so I want to create it. So yes, I've turned my minus 1 to the n minus 1 by multiplying by, or factorising if you like, or reverse of factorising. We're actually putting it in, aren't I, to raise the power. But it becomes plus minus 1 to the power of n. All right, so I've got that common factor. That leaves me with I2n plus I2n minus 2. Oh, hang on a sec. Back in part A, we worked out a result. So I can use that, but this time I'll let n equal 2n minus 2. And then when I substitute in, I'll get 2n minus 2 plus 1 in the denominator, which is 2n minus 1. All right, hey. Now we're going to show that Jm is this lovely expression. So Jm, I can use the formula that we just proved. Right, so we now know that Jn is, if I move the minus to the other side, I've got a formula for Jn. So, here we go. Jm is equal to minus 1m on 2m minus 1 plus Jm minus 1. But then Jm minus 1 will be minus 1 to the m minus 1, 2m minus 3 plus Jm minus 2. Basically, I'm just using the reduction formula over and over again. And so on and so on and so on. And eventually, I'll be left with J0. I know I can get to 0 because we're reducing by 1 each time here. Well, have a look at what we're trying to prove. There's a sum there. But if you look at each of the terms, that is in fact the sum that I'm trying to get. So I could rewrite all of those terms as the sum from 1 to m of negative 1 to the power of n over 2n minus 1. And J0, so I'll just add in J0, is the integral of dx from 0 to pi on 4, and that is pi on 4. Now use the substitution u equals tan x to show in is in fact this expression. Okay, so in integral tan to the power of n. U equals tan x is the same as x equals the inverse tan of u. It makes the question easier. Why did I do that? Probably because of the 1 plus u squared in the denominator. Because x equals inverse tan of u means dx is du on 1 plus u squared. I can now just sub straight into that. Tan to the n becomes u to the n. Dx is du on 1 plus u squared. Bang. Got the answer straight away. So in that case, it's a lot easier. Whilst they told me to use u equals tan x, I claim I did, because I started with u equals tan x and said, well, I want to rearrange it. Deduce that in is in between 0 and 1 on n plus 1, and then conclude that jn must approach 0 as n approaches infinity. Un on 1 plus u squared, we know, is always going to be positive, because remember, n is a positive integer. Therefore, the integral, it must always be above the axis, so the answer to the integral must also be positive. Now, in plus 2, remember, was 1 on n plus 1. So rearranging that. So in is less than 1 on n plus 1, because I'm always taking something away, which we know is positive. We just proved in's always positive. So if I'm always taking away something positive, in must be smaller than 1 on n plus 1. There it is, trapped. Now the limit. So the limit, therefore, must be 0. Because the left-hand side is 0, as n approaches infinity, the right-hand side would be 0. So I know the limit of 1 on n plus 1 is 0. So therefore, the limit of in is 0. Jn is the limit of minus 1 to the power of n of I2n. Well, if in's limit is 0, I2n's limit must also be 0, which means Jn's limit is also 0. Let's try some of these reduction formulas.